The subject of this week's lectures is positron emission tomography, which is the twin technology to emission-computed tomography that we dealt with last week. First, I want to start out with some examples that illustrate what this technique does. So first we'll see here, this is a positron emission tomography scan. We can see the whole subject. Here you can see the arms, and you see on the top very bright uptake in the head, and you see a lot of spots highlighted in the body. Those are metastases, and that actually in the clinical application has been a major motivation for this technique. This is the easy detection of metastasis in cancer patients. Here in this video you see also, this is a deoxyglucose uptake scan. You'll see on the top the brain, which has a lot of uptake, and the bottom you can see the bladder. We can see in the middle the heart, and you can see just above the heart this little spot there. That spot shouldn't be there. That is a metastasis in this poor patient. We have the application actually is PET-CT nowadays. You can actually nowadays no longer buy just a pure PET scanner. You buy a PET-CT scanner. And the reason is illustrated here in this example. These are transaxial scans. You can see here on the CT scans, you see bright the rib cage. You see the heart. Dark is the lung. There are no electrons in the lung, so we don't have any absorption here. And this is the heart here. So the CT scan provides anatomical resolution, and the PET scan brings functional metabolic information. And here we see in the PET scan, we see uptake here in this spot. This is not very informative to figure out what is actually going on and where, but if it's overlaid on the grayscale image, so we'll take this image, we'll take this image here, and they are all fused, color-coded the PET data, one can see very clearly where this bright spot of uptake is in the body. This is the coronal scan, so we're now looking as if we are looking at me. So you see the neck is here are the arms, and we have the corresponding PET scan, again with a high uptake. When you fuse the CT scan here on the left with the PET scan, one can see where the high uptake is. That is where the neoplastic lesion exactly is positioned. So what does a PET scanner look like? And a PET scanner is shown here. We have the scanner with a nice white cover. We don't want to expose the patient to all the physics and engineering that's behind it. So there's a nice cover that makes it less intimidating. The patient bed. Here's a holder. This is now set up for a brain scan here for the head. And this will go here into the hole where the detection is being done of the PET scan. Now, what is inside that scanner? What is inside the scanner is a detector ring, and this is very much the same technology that we discussed last week. It's the same principle of detection. We have scintillation crystals, photomultipliers, and then the electronics. The difference here is it's an entire detection ring that is being used for positron emission tomography, and we'll see in a short while why this is different from SPECT. So this goes in here. It's actually inside the cover. So let's look at a picture with the cover removed. And here is now such a scanner. We have a sphere here filled with some substance. And so here you can see the cover removed, and here we can see the detector ring. This is the patient bed. So that's what's inside a PET scanner. Here I'll give you examples of some brain scans. At the bottom we have the scans taken in 1975. One can see that it is a brain, but it's quite blurry. And you can appreciate the 20 years of technological development here. If you look now at the brain scan here and taken from 1995, here one can see very nicely the gray matter, which has higher uptake of the tracer in the brain. Now on this video here, what I want to show here is the start of the scan. So we have the patient on the bed. The bed is lifted automatically and then moved into the gurney, and the patient is preparing for the scan. So to give us an idea how this scan is being done. So these are the human scanners. The detection, as I mentioned, is very similar to SPECT, but the principle is different, and this has to do with a detection principle, and therefore this has an impact on the instrumentation of the positron emission tomography or PET scanner. Now let's look at some examples of animal models. So we have first the scanner here. So let's look at the scanner. It's a smaller scanner. We can appreciate that. This is about body height here. Here's the bed where the mouse would be placed, or the rodent. Here's the opening, and one can see from the dimensions a human would certainly not fit in here. As we've seen with CT or SPECT, the scanner that is used for animal scanning is smaller. It's adapted to the smaller size of the species being investigated, and this is the standard approach here. Interestingly, they still cover up the electronics. It's probably more for the protection of the electronics here, rather than appeasing the volunteer here, who is an anesthetized rodent. Rodents, this is a rat here. They have to be anesthetized, otherwise they start moving around. So here's the opening of the scanner, the anesthesia mask, and here we can see a scan of the mouse brain. Here are some examples we have on the left. We have the optical imaging. This is herpes simplex virus mediated imaging of gene expression. On the right, we have a tracer that images where this gene has been expressed. Here's another example of optical imaging here in the bottom, and on the top, the positron emission tomography scan. And these are the two types of tumors, one's resistant and one's sensitive to chemotherapy. If we look at a typical publication, this is a figure taken from a paper, then we have a lot of information. We have the PET scans here with this FHBG tracer, and here with the FDG tracer showing the PET images. Here are the analysis with different treatments. So what you'll see in research is that biomedical imaging here with positron emission tomography is very often an integral part of the study. So now let's come to the question, what is positron emission tomography, or PET as we call it in short term? Basically, what we are measuring with positron emission tomography, there's the word positron in there, and what we're looking at is the annihilation of positrons with electrons. This gives rise to X-rays that are being emitted from the annihilation process. This is the basic principle that is behind it. The positrons are emitted by a parent nucleus that's typically part of a tracer that's administered to the subject. So it's an exogenous substance that's not naturally occurring, which we desire to image. So we'll inject the tracer here, and the tracer distributes, as we can see here now, with the subject turning more and more red, and then we have the X-rays that are being emitted in all sorts of directions. And now we have two issues. As with SPECT, they're actually the same issues. One is, when we detect an X-ray, how do we know what its direction was? Remember, with SPECT we used collimation for determining direction of the X-rays. Here the principle will be slightly different, so we still have to deal with this question. And as in SPECT, we have absorption that is undesirable. Remember, with CT scanning, absorption was the contrast generating parameter. We irradiate the subject with X-rays and we want to see the different absorption. That's the basis of CT scanning. With SPECT and also with PET, the absorption is in principle undesirable, and it would be nice that it would not happen. So we have to consider this as a nuisance effect. So this is the situation with PET, very similar to SPECT or emission computed tomography. So the principle therefore is similar as what we discussed last week with SPECT, but there is a major difference, and you will see in a short while where this difference comes from. So if you look at the setup of a PET scanner, we have the detector ring, here's the subject, we have electronics, here's a coincidence processing unit, we have the computer for the reconstruction, and here we have the process that's at the heart of what we are detecting, and that's the annihilation of the positron. So the most widely used tracer for PET is fluorodeoxyglucose. It's the glucose where there's a fluorine attached at the 2 position. Here's the example of this diagram here. This is the 1 position, here's the 2 position. Instead of an OH group, there's a fluorine attached here. And here's the 3-dimensional graphic. In green, you can see the fluorine atom at this position. It's fluorine 18, so fluorine 18 is an unstable nucleus that decays, and as it decays, it emits a positron. So we are looking at imaging antimatter, that is the annihilation of antimatter with matter. So what is going on here? So we have the unstable parent nucleus here. We have in red the neutrons and in blue the positrons. And now when this unstable nucleus decays, there is a conversion of a positron to a neutron. So we're changing the charge by -1. We'll have a different charge. We have charge conservation. So we will have this positive charge emitted from the nucleus in the form of a positron. And this positron diffuses through the tissue, undergoes different interactions akin to the electrostatic Coulomb interaction, just like we've seen with Bremsstrahlung. And after this positron has lost most of its kinetic energy, at some point it will be attracted by a nearby electron. The two get together, they combine, it's matter and antimatter, and when antimatter and antimatter come together, they are annihilated, so there is the emission of 2 X-rays. To give you an idea, these X-rays travel at 3 × 10⁸ meters per second. So in 3 nanoseconds, the X-ray will have traversed 1 meter in the scanner. So now question, why are 2 photons being produced? Why not just 1? We could in principle have the electron and the positron combine, and from an energetic standpoint we could produce a single photon. Remember that we said that the positron and electron, the positron loses most of its kinetic energy. So let's consider the situation, idealized, that the positron and the electron at the time of annihilation have 0 kinetic energy. So the total linear momentum of the positron-electron pair is 0. If we had a single photon that's emitted, that photon would have energy. And if it has energy, as we've discussed 3 weeks ago, the photon carries a linear momentum. So if we have a single photon, we would have suddenly a net linear momentum, and this would violate conservation of linear momentum. If we have 2 photons that go in opposite direction, those 2 photons with equal energy would produce a situation with 0 net linear momentum. So this is a consequence of the conservation of linear momentum, that we need to have 2 photons. What is the energy of the photons? Well, the energy of the photons at rest, there's 2 electrons and masses of electrons, the electron and the positron, are converted to energy. So we have a total energy of MEC squared. We have 2 times MEC squared, but we have 2 photons. So one of those photons has an energy of MEC squared, and that is in kiloelectron volts, that's around 510 kiloelectron volts. I'm giving here also the conversion of electron volt into joule, if you ever wish to verify this calculation with SI units using c squared and the mass of the electron. So now what does this mean? This basically means in order to determine the location of a annihilation event, what we need to do is we need in the detector, we need to select 2 events that happen simultaneously, that is 2 X-rays that we detect simultaneously at the same time. And then we will know that if we have a detection here and a detection here, then we will know somewhere along this line there has been an annihilation of an electron and a positron. And this is the basic detection principle. As a side note here, notice here that the light travels around a meter in 3 nanoseconds. That's an awfully short time. This in general does not allow us to determine the exact location of the electron-positron annihilation process. It is too imprecise. As we will see later, the time resolution of the scanner being below 3 nanoseconds is not the typical time resolution that the detection materials provide us. So what we have here then, the principle is annihilation coincidence detection. The basic principle is we detect two photons at the same time. We attribute a location somewhere along a line that connects the two detectors, and somewhere along this line we had a annihilation of a positron and an electron. So what does this mean? It means we detect two events at the same time, and this defines the event along a line. Moreover, we do not need a collimator. So for positron emission tomography, there's the difference between SPECT and positron emission tomography. Due to the fact of annihilation coincidence detection on the two sides, we do not need to have a collimator to establish the directionality of the X-ray. This is done by the coincidence detection process. So what is coincidence detection? What do we do when we do coincidence detection? Just as a reminder, we'll start out here. We have the positron that's emitted by the nucleus, diffuses, annihilates with the electron, and produces two 510 kiloelectron volt X-rays that are going in opposite direction. We detect them simultaneously, and this establishes lines of incidence. Along this line has been the event. This simultaneous detection provides the collimation. It's electronic collimation, and this gives us the directionality of the X-rays. So let's look at the situation in a detector. We have an X-ray that hits our scintillation crystal. Here the detection principle is the same as the principle used for SPECT. This produces, as we've discussed last week, visible light. This visible light is amplified by the photomultiplier tubes, and in the end we produce an electronic signal that looks like something like this. This is what the signal that's being detected. And let's say we take these two detectors here, we have these two signals here. To determine the precise time, because we want to determine simultaneity for coincidence detection, one wants to have a precise measure of the time, and this is done on the leading edge of the amplified signal. This is steeper, so it is sharper and it has a higher first derivative. So now question, how do we define simultaneity, that is coincidence? Well, the answer could be, well, we'll just say they have to be at the same time. But what does it mean to be at the same time? In an ideal world, on piece of paper, in theory, same time means at the same time, precisely down to attosecond precision. But we're dealing with an instrument, we're dealing with imperfections, and so defining simultaneity requires a certain uncertainty that one allows. Within which time interval do we consider two events that are being detected as being simultaneous? So the situation here is in this graphic here. We have a detector A, a detector B. We detect the signal in detector A. This could be this one. Detector B could be this one, for example. And we get two signals. And now we want to determine if these two signals are simultaneous or not. So we're getting a signal A. We're detecting the leading edge of signal A, the leading edge of signal B. And then what is in practice is being done, we define a coincidence interval, tau, which has a certain value. And here for the BGO crystal, it is typically 10 nanoseconds. So anything that's within this interval here, 2 times tau, is considered as being simultaneous. So these events, if they happen within 20 nanoseconds, we would say this has happened simultaneously, and we'll consider them as being due to the annihilation process. If we now recap what the detector is made of, you see the graphic here, and you'll say, wait, this is the same as SPECT. And what I'm drawing you here is actually the same situation as what we have in the SPECT scanner. So we're looking at the gamma camera, the basic elements here. Now it's the PET camera. We have the scintillating crystal. This is unchanged. We have the photomultipliers. It is the same thing. So we have the scintillation crystal, the photomultipliers. We have also position logic electronics, a light guide. This is all the same. And here I have drawn the collimator. But wait, Didn't I just say we don't need a collimator? Well, this is the situation of what you have with the SPECT scanner. And with the PET scanner, we have said we do not need the collimator, so we can forget about this. Here's a piece of the instrumentation of the detection process that we don't need in PET scanning because we have the simultaneity of events that establishes with which we can establish the direction of the X-rays that are being detected. So what is the consequence of not having the need for collimators? Well, one consequence is that this is an increase in sensitivity that comes from that. Now, why is this so? Let's think about it. Why are we getting an increase in sensitivity if we do not need collimators? Remember, the process of collimation is brute force. We just basically say we put a material in place that blocks the X-rays that do not satisfy our geometric condition of collinearity. So what we're doing is we're taking X-rays and we're eliminating the bad guys with the wrong geometrical arrangement. So this collimation is a process of establishing directionality by eliminating all the X-rays that are not coming in perpendicular to the scintillation crystal. Whereas with positron emission tomography, due to the detection of simultaneous events, we don't do that. So we can essentially accept all X-rays that are being detected as long as they have simultaneous, that is, as long as they are X-ray pairs. So this is a major source of sensitivity increase for positron emission tomography compared to SPECT.